So in that example, you have a kind of arm. There's in the middle of the arm, there's a cut. It's a slot. And in between that slot, there's a particle. That particle can only move inside of that slot. That's a straight cut. And the particle P has a cord attached to it. One end of the cord is attached to the particle, another end is attached to one end of that cut. And everything is on a horizontal plane. That says that on a horizontal plane. So this arm and this particle are put on a horizontal plane. What does that mean if it is a horizontal plane? There's no what? Only on I direction. Okay. So if it is, that's a keyword. You're gonna see a lot of problem with horizontal plane. So I'll highlight here. If you see that keywords, that means this arm OA, OAB, this arm, it's on the table. It's put on the ground, and the particle P is just sitting on top of the table. And this arm, the rotation of arm is just, on horizontal plane rotating. It's not rotating. Even we draw like this, we're looking at the top view. This is a top view. You all learned engineer graphics, right? That's a top view. So if you look at the top view of this whole thing, that's how everything's set up. So we know the angular acceleration of that arm, it's omega. And we know weight of that particle P is 5 pounds. We also know the distance from that reference point to particle P, it's R. And the change of that distance, R dot, which is speed of particle P, it's R dot, which is negative 0.5 feet per second. It's a constant number. Also, that angular velocity is also a constant number. And we're trying to find what is the tension in that cord. So what is the tension T inside of that cord? And what is the normal contact phase on P? So if this arm is rotating counterclockwise, is the particle P going to be in contact with the surface B or surface A? And third question is this particle, yeah, that was third question. Question B is, we want to find out the contact force, the normal force that particle P is experiencing. All right, this problem can be solved by using the 6-step approach. I want you to talk to each other and to see how would you apply those 6-step approach to this example. You can work with each other on this example. Even we have an arm OAB and the particle P, the focus of this problem is that particle P. So that means you want to draw the free body diagram, set up your coordinate system based on that particle P. Think about how would you draw the free body diagram? Okay, my first question for you is how many forces would be on your free body diagram for that particle P? Use your finger, show me how many forces on your free body diagram. Someone said 3, someone says 2, someone says 4. Alex, you're always 4. What are the 4 forces? Okay. Okay. Wondering in this problem, did you mention anything about friction? Oh, it's frictionless. Okay. So instead of that slot, that's all the surface are frictionless, I think. So in your free body diagram, look at that particle is constrained by that cord. So you have a tension force from that cord. You also have a normal force from the surface. We don't know which surface. Let's assume that no normal force goes that direction. You see why I don't have my weight force? Why I don't have my weight force? Yeah, so because in the problem it says horizontal plane. That's, you also have a homework due next Monday has horizontal plane. That means you look from top to bottom, look at the table, everything is just sitting on the table. Now you're drawing free body diagram based on how things rotate from the top view. Can you see friction force from the top view? On the top view of the friction force perpendicular to our screen, so it shouldn't be on your free body diagram. In this case, the friction force goes into the screen. Okay, and how would we set up our coordinate system? I would set up my coordinate system to line up with my forces. So we use this as my J and use this direction as my I. Okay, that's step 2. I believe you can do step 3. I want to talk about step 4. So we have 4 minutes left. Okay, step 3 is forces, right? Step 4 is acceleration. We want to write out acceleration in vector form. We want to write out what is the acceleration for that particle P in vector form. The reason I said this is a good example, because if we look at this example, we have an arm and we have a particle moving inside of that arm. That's a classic problem from chapter 3, the moving reference frame problem. Can you see that? In your exam, we have a disk. We have inside of the disk, there's a cut. A particle can move inside of that disk. Same thing. So that means the acceleration here can be written as the acceleration equation we learned from chapter 3. What is the acceleration equation from chapter 3? A very long equation. Remember that? It should be on your notes. So we have to find 2 points. So AP and AO. Let's use another point O. I need to make an adjustment here. I think the distance R is measured from point O. So R is measured from point O. So AP from this is chapter 3 equation. AP equals AO plus AP/O relative. Remember that? The memory should come back. You see that relative plus alpha cos RP/O plus 2 omega cos VP/O relative minus omega square RP/O. This is just the standard equation from chapter 3. the moving reference frame. Yeah, now you can plug in everything you know into this equation to look at what is relative acceleration, what is alpha, what is omega, and you should get the expression for AP in terms of something I plus something J. I will leave this for you because one of your homework has a very similar setup. And step 5 going to be assemble your F equals MA equation. Okay, so that should help you get started on your problems homework. That's all we have today. Make sure you drop your exam 2 rework into that box.